This is Lab 4, Circuits and Capacitors by John Cutrone. The goals of this lab are to predict the behavior of circuits containing resistors and capacitors in the Circuit Construction Kit PhET simulation. The experimental current found in the circuit with two resistors is 0.02 amps. The experimented and calculated values for the current potential difference match each other. The stronger the resistance in the RC circuit, the longer it takes for its capacitor to discharge and charge. And finally, the RC time constant value is approximately 6. Some main physics concepts explored in this experiment are the node rule, where the amount of current entering is equal to the sum of the currents in two or more branching paths and vice versa, and the voltage rule, where the potential difference for voltage for a round trip around a circuit is equal to 0, as well as Ohm's law, which interconnects voltage, current, and resistance, and the two different resistance equations for resistors in series and parallel, and capacitance, which relates how much charge can be stored in a capacitor per unit of potential difference. The system is the circuit, including current and potential differences, and the surroundings are anything around the circuit, which is negligible in this simulation. Some assumptions we can make are that ideal wires and ammeters are used, which mean they don't have any resistance to the circuit, and ideal capacitors are used where they charge nearly instantaneously. In procedure 1, a simple closed circuit is made with two batteries, two ammeters, and two resistors. The experimental current found was 0.02 amps, and the calculated current was 0.0204 amps as shown below, and the reversed ammeter current is negative 0.02 amps. For procedure 2, the same model is used except one ammeter is taken out, and the predicted potential difference is predicted to be 3 volts due to the two batteries, and the predicted current is 0 amps because the circuit is open. And the experimental potential difference and current match the predicted values, which mean they agree. For procedure 3, the same model as before is used except they closed it, and different potential difference values are found at different letter points about the circuit, and if you sum them all up, the potential difference of the entire circuit matches with the expected results from the voltage rule, which is 0. For procedure 4, an ammeter is added to be in parallel to one of the resistors in the circuit, which increases it by 2.06 amps. And the reasoning behind this is that some of the current that would have gone through the 100 ohm resistor would instead go through the path of the ammeter, which has no resistance, increasing the amount of current in the circuit. Next, the resistance for the resistors, ammeters, and wires are calculated with Ohm's law, specifically the R equals V over I iteration, where the resistance was found of the 47 ohm resistor is found to be 48 ohms, the resistance of the 100 ohm resistor was found to be 102 ohms, and the resistance of the ammeter and wire were both found to be 0 ohms, so very close. In procedure 5, an RC circuit is made with the battery, capacitor, and a light bulb, where the amount of ohms that the light bulb is increased, which shows that when the resistance is higher, the amount of charging and discharging time increases. In procedure 6, another RC circuit is made with a battery, ohm resistor, and a capacitor, where the capacitor is charged with the battery is removed, and then for 20 seconds the potential difference across the capacitor is recorded. Then a natural log V over V naught versus time data set will be graphed, and the slope of this graph is equal to -1 over RC. The slope I found was -0.17, which means that the RC value is approximately. Some possible sources of error are possible estimation errors, lack of precision in the ammeters, and human error with the timing of the charge and discharging of the RC. If a real-life ammeter was used in the experiment, it would lead to a decreased amount of current detected in the circuit, because it would not be considered a negligible resistor along with wires and thus would increase the total amount of current measured. And the ideal model would predict the capacitor to charge almost instantaneously. However, the prediction will not happen in real life. Both wires and the capacitors have a certain amount of resistance in reality, which would lead to a longer time to fully charge the capacitor. Thank you.